Hello, friends, and welcome to this live stream here on YouTube. Okay. In this live stream, we are, as you might have heard from, as you might have read from the message on as you have read from the title of the video, as well as from the description, we are going to cover LeetCode graph problems. I have shared a list of problems that you can solve along with the lecture. I've shared a list of problems that you can solve along with the lecture. It's a very good idea to open that list of files, a list of questions, and solve with me. My style for teaching is going to be very simple. I'm going to present a question here in the same sequence that you have in the list of questions. And first, I'll present the question, then I'll give you some time to solve it, and then you can solve it along with me. We'll try to keep it interactive, so I will be asking you questions during the classroom. In your room, try to speak out those questions. The answers to those questions, try to speak them out loud. Okay, and I'll respond to them. In the chat, I'm going to keep the timestamps for all the questions. So if at any point you want to go back to any of the questions, you can do so at any point. We'll get started with the first question. So the first question we have is called as LeetCode 200 number of islands. LC 200 number of islands. Let me read out the question to you before explaining it on the board. In this question, imagine a grid, a n cross m grid. And in this n cross m grid, imagine a grid like this. This is M and this is N. Think of it like not just a grid, but a map of a country or the whole world. Now, in this map, there are different places which are land. All these areas are land, like this. And whatever is not shaded is actually water. So this is land, and this is water. The question asks you to return the number of islands. So in this case, the number of islands is, can you tell me? Right, the number of islands is 3. So the number of islands is equal to 3. So given a map, you have to count the number of islands. Now the question is, how is this map represented? That makes all the difference. The map is represented as a grid of 1, 0 or 1. So I'll give you a 2x2 grid or a 3x2 grid. For example, the grid might look something like this: 0, 1, 1, 1, 1, 0, 0, 0, 1. Now this grid here represents a map. That map is something like this. The ones here represent land and 0 is representing water. So if I have this as a map, it will be 2 blocks here. These are land and these 2 blocks are land and this one block is land. So these are lengths, and it is said that two lengths are consecutive or they form a single island if for a given land area, the other land area is in these 4 directions. For example, in this question, this one and this one, these two ones, although they are consecutive, I mean they are diagonally neighbors, but they don't form the single island. These two are separate islands. So how many islands do you see on the whiteboard? 3. That's what you have to find. Now that's the explanation of the question. Let me write down the exact problem statement. Given a binary grid, in this 0 is water, 1 is land, cells are connected if they share an edge. Output the number of islands. I hope you follow the question. Try to think for a few minutes about how you are going to solve this question. One idea that might come to your mind at this point is you can have the grid with you, and if you can just iterate through the grid in left to right and top to bottom direction, what you can do is you can sort of mark the preceding and succeeding cells. So if you have a grid like this, uh, in this grid you can mark that this is island number 1, this is island number 1, and then when you come here you mark this island. Just check the top and left cell, and if it is and tell us if it is belonging from the same island, then this belongs to the same island. What I mean to say is you turn this 1 as 2, and then when you come to this one you turn it to 2, and then this is 0, this is 0. When you come to this one you realize this 2 is sharing a edge, you turn it to 2, and then this way you will be able to mark the numbers by looking at top and left. But the problem with such a scheme is if you are just going from right to left to right and top to bottom, there might be a there might be an island which looks something like this. Now if island looks something like this, then this person here will not be, since you have only processed till this point at this, while you are at this node you have only processed till this point, you will be inclined to start a new island, although this is belonging from the same island. So any scheme that you are thinking of in terms of grid will lead you into different dead ends. And if your first impulse is to think in terms of grids, then stop that impulse. That's going to lead you into dead ends. So if you cannot process it index by index by iterating from left to right by row wise and column wise, how can you do it? If this was a question where you only considered uh, top and left neighbors, then probably you can do with grid iteration. But since you have to consider all neighbors in all 4 directions, iterative approach where you go from rows and columns will probably not work. The way, so what can we do? The way to do it is try to do, try to think of graphs. Don't try to think of the grid. Don't try to think the grid of just as a grid. Try to think of the grid as a graph. And once you think of the grid as a graph, You're not bound to travel in left to right and top to bottom direction. You can travel in all sorts of interesting ways. And that's the key insight of this question. What you need to do is to recognize that implicit in this grid is a graph. Let me draw a small grid and explain what this point means when I say that grid is actually a graph. So if I have 1, 0, and 1, I can think of each cell. These are 4 cells. I can think of each cell as a node. So, I'll write here graph. In this vertex is the set of row index comma column index. So that's your vertices. And what is an edge? So you will have 4 vertices. 0, 0, this is one vertex. Then you have 0, 1. Then you have 1, 0. Then you have 1, 1. These are the 4 vertices. And what are their edges? Edges are these. This vertex is connected to 0, 0 is connected to 0, 1 and 1, 0. 1, 1 is connected to 0, 1 and 1, 0. So these neighbors are forming these. And all you do is now disconnect the, first of all, once you have this graph, once you have built this graph, what you need to do next is delete all the vertices from this graph that have water. So this vertex goes away, 0 goes away, and all its edges also go away. So 1, 0, which is containing water, goes away. Delete this. And now, once you have a graph like this, all you have to do is count the number of connected components. So this question boils down to, given a graph of vertices, which is cells, and edges, which is neighbors. Uh, so not only vertices, you also say vertex row index comma column index, where grid of row column is equal to 1. So for all grid a column equal to 1, edges from our row comma column, there is a edge to row column plus 1, row column minus 1, row minus 1 column, and row plus 1 column. So those are the 4 edges, and that's the vertex, and this is the graph. Solution is number of connected components in G. So graph G, number of connected components in graph will tell you this. Now we have come to an understanding of this question where, okay, you have a graph, and this graph actually tells you about the nature of this picture, this grid. Now, the only question that remains to be answered at this point is, how do you find the number of connected components in G? And the answer to that is do a DFS from each of the cells. Just do just maintain a visited array, and for every node that is not yet visited, for every node that has not been visited, do a DFS. The number of times you have to do a DFS is going to be equal to the number of islands. At this point, I'll guide you through the code for this problem. If you have not taken the screenshot or notes of this part, please do it now, and I'm rubbing it. So there is a main function which is def number islands. This takes self comma grid. The first thing you have to do is, if grid is empty, if not grid, if grid is empty, you can return 0. Once this is done, you can do a for loop. You can keep a count of islands. So I'll just call it island which is equal to 0. Then I can do a for loop over this grid for row in range of length of grid for column in range of length of grid 0. Get the row and column. If what you are at, if grid of row column is actually 1, then you do DFS grid row and column, and once you find such a node, you do island count plus is equal to 1, and then you can return island count. So what am I doing here? I have some grid which contain, and I go over the grid, and if I come to a cell which has land, I do a DFS. What this means is mark all cells in this island as hash. So this DFS will mark all the cells in this island, whatever island this row and column belongs to, as hash, and then it will count that island as 1. So next time any of the cells will not be running DFS again. So once you run DFS for one island, for a single island, you don't run it for any of its nodes again. So that's the main function. Now the only thing that remains is how do you write this DFS? It's just very simple. So I'll try to write it here. Let me draw a line here and let me rub this. So def DFS over grid, comma row, comma column. And for this row and column, first thing you do is if row less than 0 or column or row greater than length of grid greater than equal to length of grid, or column less than 0 or column greater than equal to length of grid 0, if any of this is true, or grid of RC not equal to 1, if any of these conditions is true, you return. Okay, you return here. This is an invalid case, you take care of that. This is checking. Then once you have checked that it is a cell with land and it is within the boundaries of the grid, what you do is grid mark this as visited, and the way to mark is grid of RC is equal to hash. So this will never be calculated again. This is a visited node, and then you do DFS on grid R plus 1C DFS. Do the DFS on all 4 neighbors. R minus 1C DFS on grid R C plus 1 and DFS grid R C minus 1. So that's the overall structure of this code. Let's do a short dry run on this, because without a dry run, I'll do a dry run for this code on a small graph. So you have this, and let's say this is 1, 1, 1. Let's say this is 1, this is 0, 0, 1, 0, maybe a 1 here and a 1 here and 2 zeros. Okay, so we'll do DFS on this. Let me break it down into 5 cross 2 matrix. So that's your matrix, 5 cross 3. And we'll go over RC values. So RC. So initially R is 0 and C is 0. R is 0, C is 0. Grid of RC is 1. So we do a DFS from here. So RC is 0. We do DFS of 0, 0. When you do DFS of 0, 0, you come to this point R is 0, C is 0, this condition does not hold. So what you do is you set this value as hash, okay, and then you do go to R plus 1C, which is R plus 1C, which is this point 1 0. In R plus 1C, you do DFS of R, sorry, 1 comma 0. So here R is less than R is greater than 0, it is less than length of grid. C is also within the limits, but grid is not equal to 1, it is equal to 0. So you return. So this does not do anything. So this returns. Then you do R minus 1C. So R becomes minus 1, C becomes 0. When you do DFS of minus 1 comma 0, what happens is DFS of minus 1 comma 0. What happens is R is less than 0, so you return. So that is also not valid. After this point, R minus 1C, you have RC plus 1, in which case you have R is equal to 0, C is equal to 1, which is this point, DFS of 0, 1. When you do DFS of 0, 1, they are within the limits and RC is actually equal to 1. So you set it to hash and then you go deeper, one more step deeper. When you go one more step deeper into this, what happens is you have R is equal to R plus 1C, which means 1 comma 1. When you go to 1 comma 1, you have the DFS of 1 comma 1. Once you do the DFS of 1 comma 1, you again set this as hash, and then you go one step further. You go to R plus 1 and C, in which case 2 comma 1, and you do DFS of 2 comma 1. Now 2 comma 1 is here, and you set it up as hash. Then once you are at 2 comma 1, all the other calls will return because both sides there is water. So you will come back from this. You have marked these two as hash. Similarly, you will come back from this. You'll marked as hash, and then you will do R minus 1C for 0 comma 1, which is going to give you R is equal to minus 1, which is also going to return. Finally, you will do R comma C plus 1, which is 0 comma 2, and once you do DFS of 0 comma 2, you will come to this point. It will pass the case and you will mark it as hash, and rest of its nodes will also come back. So this way you will process this whole island, and similarly you will say uh, count of island count is equal to 1. Next time you come to this one, you will set it as hash, you will set this as hash, and then you will mark count as 2, and then you will return 2 as the answer. So that's how you can structure the code for number of islands problem. Give it some time, try to think about the code, and try to see if you can explain this code to somebody. Yeah. This is how we can solve the number of islands question. Now let's talk about the next question. This question is LeetCode 133 clone graph. LeetCode 133 clone graph. Given, let me read out the question first, and then once I have read out the question, I'll explain it on the board, and then you will understand it completely. Given a reference node, given a reference of a node in a connected undirected graph, return a deep copy, a clone of the graph. Each node in the graph contains a value int and a list of nodes of its neighbors. You are given the node of a graph, you're given a node of a graph, and you have to clone that graph. So let me talk about the test case format. For simplicity, each node's value is the same as the node's index, and it is one based indexing. For example, the first node's value is 1, second node's value is 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in a graph. Given the node will always be the given node will always be the first node with value is equal to 1. You must return the copy of given node as a reference to the cloned graph. Okay. Let me walk you through this question. So this is an undirected connected graph. Given an undirected connected graph, given an undirected connected graph through a node reference create or create a deep copy of the graph. Now, if I can give you the adjacency list of the graph, this question becomes a simple question where you just take a deep copy of the grid called as adjacency list. But the problem is you don't have access to the adjacency list. You only have access to a node reference. And how does the node look like? The class node the class node contains two things. First is value and the other is list of neighbors. You have access to the value of the node and the neighbors. And the neighbors list is a list of nodes. So this here is an int and this here is a list of node. How can you create a deep copy? Now what you are asked to do is, let's say I give you a graph whose node 1, let's say you have a graph like this. You have to create a copy of this graph, but you don't have access to the adjacency list. You only have access to this, and you have to create another copy 1 dash 2 dash and 3 dash, where each of these nodes are created, and for each of these nodes you have the list of neighbors, and you return me this node. That is the ask in the question. Given a graph through the reference to a node, create a copy, and then return the reference to the same node. How will you do this? Let's do a DFS and try to see how this copy will work. If this was a simple graph with a single node, let's say you had only one as the node, you can directly create a clone of it and send it back. So far, it is good. But if you have a node 2 here, you have to recursively clone this graph and point the have this 2 in the list of neighbors for 1 dash. So this graph will be cloned separately. So this will be cloned like this, and then you will have to create an edge here. Similarly, this will recursively call for 3. So you will have a separate graph here. This is part of a larger graph. Now 3 gets cloned here, 3 gets cloned here, and then 2 starts pointing to it. The idea is very simple. Start from the first node, clone it, and recursively clone its neighbors, and make the connection of this clone to the cloned neighbors. Uh, so the function, the DFS function returns the clone of the graph from this index and this node, and then what you do is for every one of its neighbors you create a cloned copy of it and map the cloned copy of this node with the cloned copy of the neighbors, so on and so forth. Recursively you can solve the question. So I'm now going to walk you through the code for this. If you think you can write the code for this algorithm, or you want to try the code for this algorithm, you can jump to the next question in the timestamp and try writing the code and come back to this question later on once you face a issue or once you are not able to move forward. So here is how this code looks like. You have a class called as solution. This solution class just give me 1 second. Yeah, you have a solution class. You have a class called solution. In this you have a def called as clone graph. This takes self comma node, and we'll use the same function again and again to create the neighbors. We'll create a sub function in this to get the neighbors. First, if node is none, return none. Return none. Let me define a DFS function, and before defining a DFS function, let me define a map. I call it copied. This is the map. Now I define a DFS. This takes a node and what does it do? If this node isn't copied, you return it. I'll come to this bit later. Then if this node is not being copied so far, what you do is uh, you create a clone of it. So you just call it clone. This clone is node dot val comma empty array. So it's an empty clone, and then you do copied of node is equal to clone. That's the instantiation. And then what you do is, for all neighbors of this node, you have to copy those neighbors also. So for neighbor in node dot neighbor, for neighbor in node dot neighbors, what you do is clone neighbor, clone neighbor is equal to DFS on neighbor, and then what you do is clone dot neighbors dot append cloned neighbor. So this is going to create a list of all the neighbors for the cloned item, and this DFS will return clone. So return clone. Now to save yourself from getting into an infinite loop, what you do is, if node in copied, if node is already being copied, you return the copy of the node. You return copied node. If you do this, you're going to get a copy of the whole graph. In the end, you just return, for this function here, this function will return, can you guess what? Yes, this is going to return DFS of node. The base node DFS you will return here. So that's the code for cloned graph. I can show you how this works on a small graph. Let's say you have 1, 2, and 3. So first what will happen is, you will and I'll have this copied list. So first you do is, you call DFS on 1. So DFS on 1. When you call DFS on 1, 1 is not present and copied. So you come here, you create a clone of 1. So you create a clone of 1. Hello? Yes? हो गया आपका चश्मा? Okay, okay. So this is the clone copy of 1. You'll do DFS on 1. Then copied of 1 becomes the copy of 1. Then for neighbor in node.neighbors, neighbor of 1 is 2. So neighbors of 1 is 2. So what you are going to do is, you will create a copy, you will do a DFS on 2. You'll do a DFS on 2. Now 2 is not part of copied. So you'll come here and create a clone and point it to 2. So here you'll create 2 and you'll have 2 dash. Now you'll go to the neighbors of 2. Neighbors of 2 are 1 and 3. So 1, 3. So you'll first go to neighbor of 2, which is 1. You'll go to the DFS of 1. DFS of 1. DFS of 1 goes here. Node is in copied. 1 is in copied. So you just return 1 dash. So this 2 will have 1 dash as its neighbor. You are going to append 1 dash here. Then you go to the next neighbor of 2. The next neighbor of 2 is 3. 3 is not part of copied. You'll do DFS of 3. You'll do a DFS of 3. 3 is not part of copy. You'll create a copy of 3 like this, 3 dash. And once you do that, you go to the neighbors of 3. Neighbor of 3 is 2. Now you see 2, you will do a DFS of 2 here, and 2 is part of copied. So you'll return 2 dash. Once you return 2 dash, you will append 2 dash in the neighbors of 3 dash. And then what you will do is, once you come back from 3 dash, once you come back from this, you will return 3 dash. And once you return 3 dash, you will append it to the list of 2's neighbors. So this will become 3 dash. And finally, 2 dash will return. 2 will return 2 dash. And that will become the neighbor of 1, which is 2 dash. So finally, you will have a graph which looks like this. 1 dash, 2 dash, 2 dash, 1 dash comma 3 dash, 3 dash, 2 dash. Once you have this graph, you can return 1, and that's how you solve the question. Make sense? So that's how we can solve the question called as clone graph, LeetCode 133. That's it for this stream of the video. We'll continue this stream with more questions as we go along. Today, we basically focused on DFS and looked at 2 examples of graphs problem that use DFS. As we go along, we'll do more and more problems using different algorithms, and I hope to see you in those sessions. Thank you.